Today we're going to tackle a concept that for centuries seemed completely absurd, but turned out to be one of the most powerful tools in all of mathematics and engineering. I'm talking about imaginary numbers. So let's dive in and see how an idea that sounds made up is actually essential.
Okay, right off the bat, we hit a wall. Think back to school. We all learned that a positive number times itself is positive, right? And a negative number times itself is also positive. So how in the world can you find a number that, when you multiply by itself, gives you -1? It seems totally impossible.
But this feeling isn't new. Back in the 1700s, even something as simple as negative numbers was considered bizarre. The mathematician Francis Maceras said they darkened the very whole doctrines of the equations. I mean, how can you have less than nothing? It was seen as a useful fiction back then, and that is the perfect way to think about where we're headed next.
So, just like the puzzle of 3 minus 4 forced us to invent negative numbers, equations like x squared plus 9 equals 0 created a new wall. If you rearrange it, you need x squared to be -9, but with the numbers we had, that was a dead end. So what do you do when the rules just stop you? Well, you invent a new piece for the game.
This is where mathematicians made a really bold move. They basically said, okay, let's just pretend a number exists that when you square it, you get -1. We'll call it I. Now, it's not something you can count on your fingers, but just like negative numbers, it's a useful fiction that lets us solve these impossible problems. And as we're about to see, it describes the world in a whole new way.
The name imaginary really didn't do it any favors. The legendary mathematician Carl Gauss even pointed out that if we had just called it something like a lateral unit, something that moves sideways, instead of an imaginary one, we could have saved centuries of confusion. It's not imaginary, it's just in a different direction.
And this whole idea of a new direction, it isn't just a small patch to fix a problem. It's a fundamental upgrade to our entire number system. We're about to break out of the single dimension we've known our whole lives and step into a brand new one.
Think about it. Before, all of our numbers lived on one single line. You could go left for negative, or you could go right for positive. That was it. But by introducing I, we've basically added a second axis, an up and down dimension. We've literally gone from a number line to a number plane.
This new two-dimensional world is called the complex plane. Sometimes you'll hear it called the Argonne diagram. This is the brand new home for our upgraded numbers, and just like any map, it has its own set of coordinates. So a number in this plane isn't just one number, it has two parts. The official name is a complex number, and it looks something like a plus bi. The a part is the real part. That's just how far left or right you go, like always. And the b part is the imaginary part. That's how far up or down you go. Honestly, it's just like a regular set of coordinates on a graph. So a number, like, say, 2 plus 7i, isn't some weird abstract thing anymore. It's simply the point on the map at coordinate 2, 7. You just go 2 units along the real axis, and then 7 units up the imaginary axis. That's all there is to it. And what's cool is that every complex number has a partner. It's called its conjugate. And you find it just by flipping the sign of the imaginary part. So if you have 2 plus 7i, its conjugate is 2 minus 7i. Visually, it's just a perfect mirror image, reflected right across that main horizontal axis. A simple, elegant reflection.
But here's the thing. This new dimension isn't just for plotting points on a map. This is where the magic really happens. By adding this second dimension, we've unlocked a completely new mathematical action, rotation.
And that brings us to the most important question of all. If I represents this new up and down dimension, what does multiplying by it actually do? Well, the answer isn't just a new number. It's a movement. Let's just walk through this. Imagine you're standing at the number 1 on the real axis. Now multiply by I, and bam! You rotate 90 degrees counterclockwise and land on I. Now do it again. Multiply by I again, and you rotate another 90 degrees, and where do you land? On -1. This is it. This is why I times I equals -1. It's literally a 180-degree turn. Do it twice more and you complete the full 360-degree circle, landing you right back where you started, at 1. So here's the crucial takeaway. Multiplication in the complex plane is rotation. This is the superpower that complex numbers give us. All of a sudden, any problem that involves spinning or rotation can become a simple multiplication problem.
Check out this real-world example. Let's say your boat's heading is represented by the number 3 plus 4i, and you want to turn 45 degrees. Now before, you'd need all this complicated trigonometry, but now, it turns out that a 45-degree rotation can be represented by the complex number 1 plus I, so you just multiply them. That's it. You do the algebra and you get -1 plus 7i. That's your new heading, a super complex rotation problem solved with basic multiplication. It just works.
And this incredible power of rotation shows us that these numbers are way more than just a clever trick. They're like a key that unlocks a hidden, beautiful, and deeply interconnected structure within mathematics itself. And that hidden structure is revealed in what many people consider to be the most beautiful piece of mathematical art ever created. It's an equation that ties together the entire universe of numbers in a way that's just breathtaking.
Here it is, Euler's identity. Just look at it. It connects the 5 most fundamental constants in all of math. You've got 0, 1, pi, e, and our new friend, I. All of them together in one simple, perfect equation. This shows that these numbers aren't random or separate at all. They are deeply, fundamentally linked, and I is the bridge that connects them all.
Which kind of leaves us with this one last thought. If a number that started out as absurd and imaginary can end up revealing such profound truths about the structure of our universe, well, it makes you wonder, what other strange ideas are we just one creative leap away from discovering?